All right, thank you. Let me start thanking the organizer for giving me the chance to talk about our progress on, we made a D-Wave in developing a framework for machine generative modeling that is suitable to quantum annealing, but I should say not limited to quantum annealing. And if you are interested in all the technical details that I'll sweep under the rug, have a look at this paper. I mentioned my colleagues that were mostly involved in this work, but goes without saying, I wouldn't be here without all the people that work at D-Wave. So I will start with a big picture, which is good to remind us why we do what we are doing. And I think we all agree that we want to know how to use current and future generation quantum devices to perform state-of-the-art computations. And with state-of-the-art in this talk, I mean computation that apply to large-scale, complex problems, real problems, and that are competitive with the best available classical algorithms we have so far. And I think the consensus is that we need to develop quantum classical hybrid algorithms. So a quantum variational autoencoder, if you want, is a quantum classical hybrid generative model, which is suitable for quantum annealing devices. The strategy we have with this project is the following. We want to demonstrate these models are state-of-the-art in the sense I mentioned before. We want to demonstrate that these models can be trained using quantum annealing devices, and we want to do this on non-trivial datasets, such as Ames, Omniglot, but importantly on real problems. And 3, we want to identify a path to get a quantum advantage by working on realistic applications and with existing quantum devices. And this is a point that Steve Adachi emphasized in his talk. And I think it's critical for us to do R&D on real applications to learn the right lessons. So by the end of the talk, I hope I'll convince you that we have evidence we did the first 2, and we are working on the last point. So just to give an idea of what's the development in training generative models with quantum annealers, the first thing you can try is to train quantum Boltzmann machines with quantum annealers. And this you can think of as a not hybrid algorithm. And it's well known that sparsity is a major limitation here. And if you try to train these models on MNIST, you get something like that, which doesn't look like a lot like MNIST digits. You can do better if you think in terms of hybrid algorithms. And one first nice attempt was these quantum-assisted Helmholtz machines by the NASA group. And you see things get better, thanks because of the hybrid nature of the algorithm. But this model cannot be scaled very well. It lacks a well-defined loss function. It leads to inefficient training. So our approach is to use a different model, which we call QVAE. It's still a hybrid algorithm, but it allows us for efficient training, and I think it gets us closer to state-of-the-art generative modeling. And all of the images that you see here are generated with numerical simulations in which there is an RBM, which has an underlying connectivity, which is a camera connectivity. And so you see we can, as you will see later, get much better results. So what is a quantum variational autoencoder at a glance is this. There is a classical autoencoding structure, which is usually implemented with deep neural networks, and this is a classical, stress again. And then we have a quantum prior. The quantum prior is a generative process which involves sampling from quantum distributions. And obviously here we want to achieve this with quantum devices, for example, with quantum annealing devices. And a very important third point, we want this framework to be efficiently trained. We want a framework that can be efficiently trained from the beginning to the end using well-known techniques such as stochastic gradient descent. I will go in a little bit more technical detail, but promise you it won't be too much. For those of you who are interested, variational autoencoders are directed generative models with latent variables, and the way we represent being a directed model is simply a way we specify the conditional relationship between variables. We have what we call prior, which is a probability distribution defined on the latent space, and what in the machine learning jargon is sometimes called decoder, which defines the conditional relationship between the latent space and the visible variables. And the goal of these models is to reproduce the data distribution by marginalizing over the latent variables. And generative models with latent variables have a lot of nice properties. They can be used to encode useful representation of the data in the latent space. And this is something that is very important if you do unsupervised or semi-supervised learning. The problem with this model is inference, which means doing the sum written there, which is typically intractable. So the way variational autoencoder attack the problem is by doing variational inference. So instead of trying to calculate the exact posterior, we introduce a variational approximation, which we also call encoder. And we introduce a set of additional parameters phi, which are the inference or variational parameters. And we train the model by adjusting the generative parameters and the variational parameters at the same time. If you do that, we can train these models by going from training the likelihood, but to training variational lower bound, which is called evidence lower bound. And it can be shown that this quantity is a lower bound to the likelihood. And this is a very useful property. So the evidence lower bound is now a tractable quantity. And an important technical property of variational autoencoder is that, for those who are interested, we can use a reparameterization trick to express the derivatives of this expectation in a way that is efficient, has lower noise, and this is a technical trick, but for those of you who are interested, is critical to the success of variational autoencoders. A quantum variational autoencoder is basically a variational autoencoder in which the prior is implemented as a quantum Boltzmann machine. And we want, of course, to take advantage of quantum annealers to have a physical implementation of a quantum Boltzmann machine for fast sampling. We need to generalize the representation trick to discrete variables, because this is what we have if we want to have a Boltzmann machine. And this is actually non-trivial, and there are many frameworks that have been developed at D-Wave that allow us to use the reparameterization trick with discrete variables. And we will use a couple of models in this talk. Another technical element of quantum variational autoencoders is the fact that in the elbow, there is a term which is a quantum cross entropy, which is basically the log probabilities of the quantum Boltzmann machines. And as I was mentioned before in our first talk, these two terms lead to the positive and negative phase. When we take derivatives, the negative phase can be computed via expectation. The first one is intractable. But thanks to the Golden-Thompson inequality, we can derive a lower bound, which can actually compute via expectation of the energy. Basically, here we take an expectation of the Hamiltonian in which we basically ignore the transverse field. This allows us to do training by maximizing a further lower bound to the elbow. So this is good because we have a tractable quantity and we can do training. There are some drawbacks, like we cannot train, for example, the transverse field, but we treat it as a hyperparameter. So here we have trained quantum variational autoencoders with quantum Boltzmann machines, and we see that when the transverse field is large, even if the quantum is much, the bound is very loose compared to the elbow, we can still train this model efficiently, and this we can validate visually if we use these models as generative models, and we do that on MNIST, for example, which is a set of handwritten digits that is typically used in machine learning applications, and we see that we get good results with these models. So it's training these models with, for example, quantum Monte Carlo. It's very slow, and it's difficult to understand how the performance of this model scale up unless we try to do that with quantum annealers. So we go to the classical limit. We now use classical Boltzmann machines, and we scale up the model. And we see that, as you expect, performance grows with the size of the RBM we implement in the latent space. And I'm plotting here on the left the likelihood of this model. And just to give you a reference point of what these numbers mean, I show here on the left and the right the samples that are generated by these models. And you see that the quality of the digit improves when we go from a small RBM to a large RBM. And when we have large RBMs, the digits generated by the model are indistinguishable from handwritten, from digit written by humans. I want to stress that this is a vanilla implementation of these models. We have feed-forward neural networks, a few hidden layers. We get close to IT3, and to give you another reference point, the best result ever got on MNIST, which involves convolution and continuous latent variables, is like 79. So we get close to state of the art with these models, and we are now interested in what happens if we have physical connectivities. And we want in particular to study the effect of implementing higher connectivities with higher densities. So you're of course interested in the wave quantum annealers connectivity. On the left you have the chimera graph, and on the right you have the connectivity of the next generation quantum annealer. And we have trained these models on this connectivity, and here you see the result. The red line is a model which is trained actually without any connectivity, and this is our baseline. So there is no non-trivial process here taking place in the latent space. And then you see the results improve monotonically when we increase the density of our graph. But the critical point is that independently of the size of the latent space, in this case, independent of the size of our quantum annealing device, and independently of the connectivity, we can always improve beyond above a baseline, which is already non-trivial. And so this allows us to use current devices to, in this case, train on a highly non-trivial data set. And the next step here is to try to understand how we can improve how can we adapt the classical autoencoding structure to fit actually the properties of and the connectivity and the specification of the hardware to improve these results. And just to give an example that this is possible, we have considered, for example, a modification of the encoder. So we created a more powerful approximation to the posterior by including this, introducing this conditional relationship between the latent units. This allows a better variational approximation, and you expect results to improve for all cases. This is the figure I showed before with one hierarchy, and on the right you have the results with two hierarchies. But you see that some implementations are more sensitive than others to this modification. So the case without connectivity and the chimera case, the case without connectivity seems to benefit a lot from this, while, and so Pegasus connectivity improves a lot, while fully connected RBMs and chimera doesn't seem to benefit a lot. So this is something we still try to understand and to exploit to improve our classical implementation to actually fit the hardware. And to give you an example, another example, we have done the same, and we have tried to improve performance on chimera. And now we have two, as I said before, groups of hierarchies. Our latent units are divided into groups, and there are two natural ways to map these two units into chimera graph. One is to follow the bipartite structure of the chimera graph, and another one is to follow, to to follow the distinction of physical qubits in the camera graph as vertical and horizontal qubits. And we see that the implementation which we call chains, it allows us to improve results by a lot in this sweet spot. So this is just to give you an evidence that, or a proof of principle that by working with a classical autoencoding structure, we can improve and we can adapt our models to existing devices. So next, we want to understand how we can train these models with, if we can train these models such with samples coming from quantum annealers. And we have done that, and those you see on the right are digits generated by samples that are generated with a D-Wave 2000Q. And they look nice. If you compare this digit to a digit generated by numerical simulations on the same connectivities, where we turn off the connectivity and turn on the connectivity, you may see some improvement, but it's not obvious. And the reason is that we have an improvement over a baseline which is non-trivial. And we have to understand, is that improvement there? So visual validation, at least, is yet not possible, or it's kind of tricky. So we want to have a better metric for it. So we do this by validating our results via an auxiliary RBM. And what that means is the following. The term that we cannot compute when we train these models with a quantum annealers is the cross-entropy term. And this is because the probabilities of the quantum processing units are not known, if you think of it as a black box. So what we do, we train an auxiliary RBM on the QPU samples, and instead of using this untreatable or uncalculable cross-entropy, we use the cross-entropy that we derive from the RBM. And by using this quantity, we can estimate the likelihood that we obtain with our model, and we can prove, we can give evidence that we successfully trained these models over a model without connectivity. And here you see Ames digits generated by the hardware when we train with camera or without training the connectivities. So this gives evidence that we have trained these models with the hardware. And this also gives us a path toward a quantum advantage with quantum annealers. It goes through two basic lines of research. One is, of course, processor development and improved sampling quality. And uses all the new techniques and that we have, that has already been developed, and in the future develop tensor connectivities and improve coherence. But it also goes through model building. So we want now to, we have a model that is made of a classical and quantum parts, and we want to offload, if you want, generative capacity to the quantum process. And what we want, of course, to exploit larger number of latent units to improve the performance of the model. So just to conclude, I hope I showed that quantum variational autoencoders are powerful generative models which can achieve state-of-the-art performance of complex dataset, can be trained in presence of strong quantum effects. They can be seamlessly integrated with current generation quantum annealers, and we can actually and they can actually be successfully trained using D-Wave 2000Q annealers. And with this, I conclude my talk. Thank you.
All right, thank you very much. So one question I think we have time for, if there is one. So, back there. Got it.
Do you have test set fidelities for your autoencoder? So if I give you a handwritten number, with what percentage can you predict what it actually is?
So you are, I think, referring to doing classification or supervised learning? like you want to classify the digits. So we haven't done that. What we are doing is generative modeling. So our purpose here is to reproduce or learn the underlying data distribution. But these models can be used for supervised learning. If you, for example, imagine of doing supervised training on the latent space. So that's like a next step. That's why I mentioned one of the nice properties of training generative models with latent variables is that they can be useful for supervised learning tasks, such as classifying digits in this case.
All right, perfect. So let's